um, bending and the plastic flow rules. So plastic bending and plastic flow rules we have gone through in the last two sessions. So now we focus on the plastic design of beam structures. So here you can see that all right. So many practical applications when you design structures, okay, it is beneficial to allow beam structures to carry bending loads into the plastic range. So there's no need to have the safe fields only in elastic region, but it may be advantageous even if the load is increased so that the structure can slightly enter into plastic range, and that means plastic deformation. So here, during the plastic deformation, actually, the structure remains functional. So the structure will be remaining functional. So this is just to say that uh, increasing the load on the structure, even beyond elastic limits, is beneficial many a times. So even when there are small deformations of the structure, so that is what we are going to study under plastic design. So if you want to design beam structures, when the load actually exceeds the elastic limits, so even exceeds the safe field limit. So here, when the loads are increased, so we say that we are designing the structure for plastic loads. Okay, so here without collapse. So you know that stress strain relationships. So beyond the ultimate stress, the structure will rupture and collapse. So, but here we are within the plastic limits, and we will see how the structure can withstand loads even when the bending moments acting are the maximum bending moments. Okay, so the studies related to plastic design of beams, so we'll be going through now. So when in the last sessions, we discussed that when the bending moment acts, so the fibers with respect to the neutral axis on the upper side and bottom side, they start yielding. So yielding always starts from the top or from the bottom with reference to the neutral axis. So when uh, the movement actually is maximum, that is when the movement enters into plastic movement. Okay, so there are some parts on the structure, so they tend to be fully plastic. So when the bending moment is not uniformly distributed throughout the structure, but at some points uh, the structure tends to be fully plastic, and some points the structure may not be fully plastic. Okay, so the points where the structure reaches fully plastic, then the points they behave like hinges. Okay, so we call the hinges or the points where the plastic moment is full. That means it reaches the fully plastic state. So the plastic moment is at the highest point. So now we call these particular parts are plastic hinges. So when we design beams for plastic things, so we'll be focusing on whether the plastic hinges are developed on the structure or not. So now let us say the plastic hinges are formed at load points where the loads are maximum and also at support locations. So the maximum yielding takes place due to the loads acting on the structure. So, but the maximum yielding starts exactly where the load is acting, the concentrated loads, and also at the support locations. So we know the support locations includes the pin joint, the roller joints, and also the fixed joints, right? So the maximum load and maximum movement occurs at these points where the load is concentrated or where there are supporting reactions. So normally we denote the plastic hinges with a small open circle. So plastic hinges are denoted by by a small open circuit. So in the last session, we have seen that if there is a structure like this, okay, a cross section. So when this is subjected to movement, okay, bending movement, so the yielding starts, okay, from the top of the fiber and at the bottom of the fiber. So this is where the yielding starts, and actually part of the beam becomes plastic and part of the beam becomes elastic, right? So when the beam is fully plastic, so when the cross section is fully plastic, so we can denote that the entire uh, structure above the neutral axis is in plastic state, and also the entire structure below the neutral axis is also in plastic state. So this is the case of fully plastic state. Okay, so this is the state where partly elastic and partly plastic. So when the beam is subjected to increasing loads, so the bending moment also increases, and the plastic bending moment refers to where uh, the load application is maximum and where there are support locations on the beam. So those are the points on the points on the structure which reaches fully plastic state first. Okay, so we define the fully plastic movement as the plastic hinge. So when a fully plastic movement develops on the structure at a particular point, yes, teacher, I'll record. All right, so we are talking about now the plastic design. So plastic design of beams refers to, after studying plastic flow rules and plastic bending, so now we talk about plastic design. So plastic design is mainly studied in terms of plastic hinges. So what is a plastic hinges? A plastic hinge is when the beam is fully plastic, okay? And the fully plastic conditions occurs on a mechanism or on a structure at points which are support locations or where there are concentrated loads are applying. So we need to look for plastic design mainly in terms of where the load concentrations are taking place and also where the support locations are there on the structure. And based on that, we can calculate the plastic loads. All right, so now the first part of plastic design refers to identifying the plastic hinges. So we need to identify the plastic hinges. So these are the plastic hinges which actually supports the maximum moment. So when the movement reaches the plastic movement, okay, so then on the structure where there are support reactions or where there are concentrated loads, so they will develop plastic hinges. Okay, so once we identify the plastic hinges, then we can actually look for study what will be the limit load the structure can withstand. So limit load refers to the load which is sufficient to cause the structure to behave as a mechanism. Okay, so this is also called as the collapse load. So now let us look at some examples to understand more about this plastic design. So plastic design is basically identifying the plastic hinges first, then uh, calculate the plastic load. So when the mechanism, the points on the mechanism reaches fully plastic state. So now let us look at this particular beam, so which is pin connected at point A and roller supported at point C, and there is a load acting at point B here. So AC is the horizontal beam. Okay, the total length of this beam is L, and you can see the concentrated load is at a distance 3L over 4 from point A and L over 4 from point C. So we know these distances. Okay, so the first thing is when this load increases to plastic load. When the load increases to plastic load. So what happens? There are plastic movements created at points. So the first point we can expect to get a plastic movement is where the load is acting. Okay, so the other 2 points can be where the load is supported. So where there are reactionary forces acting on the mechanism. All right. So now you can see here. Now, we draw the free body diagram for this. So due to the load P at point B, so we expect the reactionary forces acting at point A, which we call it as FA, and at point C, we call it as FC. So these two reactionary forces due to the applied load P. So we can easily calculate based on the distances here by summing the moments to at A to 0. Then we can write the moment due to the force Fc at A is Fc into L. Then the moment at for the load P, okay, at A is 3L by 4 into P. So the distance multiplied by the perpendicular force. So from this, you can see that the force acting, the reactionary force acting at C is 3P over 4. And as a rule, so the difference force, the balance, the sum of the forces must be 0. So when you apply the sum of the forces as 0, then we can write the force at A plus force at C plus so if you consider upward forces as positive, then minus P is equal to 0. So when you apply the sum of the forces acting on the system is 0, then we can see the force acting at A is P by 4. So the reactionary force acting at A is P by 4, and the reactionary force acting at C is 3P over 4. So we can easily find out these reactionary forces by applying the equations of equilibrium, which we have studied in the last term under solid mechanics too. Okay, so now we study that when the load P increases to the plastic load, when the load increases to plastic load PL, okay, so then we can see, okay, so we can see that there's a plastic hinge developed at point C. So point C is where the plastic hinge is developed. This is the first place of collapse because A and C are supported. So the structure will not fail at A and C, but the structure will fail at where the load is acting. So that is point B. So we can expect at point B the plastic movement MP when the load increase to plastic load. When you're increasing the load and the load reaches to the plastic load, then the plastic hinge develops at this point. Now, what you see here is an exaggerated version of the deflection curve. So this is how the deflection curve looks A to B and B to C. But this is highly exaggerated, but you can see that the plastic hinge develops at point B. Okay, I clear this. So the plastic hinge develops at point B. So at this, so we indicate the plastic hinge with the open circle. So you can see this is the open circle represented at point B. So the movement acting at this point is MP. Okay, this is, we call it as the plastic movement. So that is the maximum movement. So now we need to calculate this maximum moment. Okay, so to calculate this, now we can, so this plastic moment develops, then the load is called the plastic load. So when the load is plastic load, then you can calculate the plastic moment as so when this load becomes So you can see the reactionary loads are also represented with PL. They are no longer P because the load increased to the plastic load. So here at A and C, the reactionary forces are also the PL, the plastic loads. So now under this, so now to calculate the plastic moment MP, so you can see that the load PL by 4 into the distance, perpendicular distance where the plastic moment is acting. So you can write the plastic moment at B, the plastic hinges, when the load is PL. So you can write PL by 4 into 3L over 4. So 3L over 4 is the distance here. Okay, so force multiplied by the perpendicular force. So that gives you plastic moment. So from the plastic moment, then you can simplify this. So this will be PL, I'm sorry, PL into 3L over 16, okay, is plastic moment. So from here, you can write, we are interested to find out what is the plastic load, okay? So you can see that the plastic load is 16 times plastic moment over 3 times L. L is the length of the beam. So this is how we can calculate the plastic load, okay, for a simple beam, okay, which is supported at A and C, and the load is acting at point B. Okay, so so based on this plastic load, then you can come out with appropriate safety factors, and you will be able to design the beam for increased loads. Okay, so the design refers to coming out with an expression for the plastic load. So in terms of the plastic moments. All right, so this is an example, how we can calculate on a simple system like this when the system is subjected to a load P, and when the load keeps on increasing and the load reaches the plastic state, then we can see that there is a plastic hinge developed at B. Okay, so that means the beam reaches fully plastic state first at point B. So the other parts of the beam are not in fully plastic state. Only the plastic state occurs at point B. Okay. Now at this point, so the moment acting at this point, we call it as the plastic moment. Okay. So we need to calculate when this plastic moment, when the load is maximum, and that load is, we call it as plastic load. So we can derive the expression for plastic load as we have done here. So the plastic load in this scenario will be 16 times plastic moment over 3 times L. So now you can see that from this particular formula, so as the length increases, okay, the plastic load decreases. As the length increases, the plastic load decreases. So similarly, as the length decreases, the plastic load can increase. So here the plastic load directly inversely proportional to the length of the beam, and directly proportional to the plastic moment. All right, so this is how we can calculate the plastic load on different types of structures. Now let us look at this beam here. This beam is subjected to it's a beam which is fixed at point A and supported at point C, and there is a load acting at point B. Okay, so the total length is L, and we know the distances A to B is 3L over 4, and B to C is L over 4. So the beam is fixed at point A. So now you're asked to find the magnitude of the limit load, so corresponding to plastic collapse. So that means if the load increases to plastic load PL, so we need to visualize okay, where the plastic hinges develop. So which part of the beam develops plastic hinges? That means which part of the beam becomes fully plastic first. So we know that the beam as the deformation continues, the entire beam will not be plastic at the same time. So different parts of the beam will be at different levels of plastic deformation. But the plastic deformation becomes maximum and fully plastics where at particular points where the load reaches the plastic load. So these are the points where the concentrated loads are acting, and are also the points which are pin connected. Okay, so different types of connection will yield fully plastic state first. All right, so now in this case, you can see here, okay, so as the load reaches to plastic load, okay, so the plastic deformation commences because this is a fixed end, okay, A. This is not supported, but it is fixed. And PL at point B is another plastic hinge. So the two plastic hinges can be developed at point A and point B. Okay, point C will not reach fully plastic state because it is supported, and let us say the reactionary force or the force at this point is given as C. All right. So when the load keeps increasing and reaches plastic load, the structure will have two plastic hinges, one at point A and another at point B. So these are the first points on the structure to reach fully plastic state. All right. So under this, now we need to find out what will be the reactionary force acting. So in terms of this load PL. Okay. So let us first calculate. So we take the free body diagram. So when the load is plastic load, so we calculate what is the reactionary force at C. So the moment developed at point B will be the plastic moment, MP, subscript P. So here we can say that now within the structure, the sum of moments acting will be 0. Okay, so sum of moments acting will be 0. Therefore, plastic moment minus. So the moment due to the load RC will be, so RC into L by 4. Okay, so sum of moments acting within this cross section will be 0. So I go back. So in this cross section will be 0. So that means MP, then what is the moment due to this RC? So RC into L by 4. So that is what you can see here. So sum of the moments acting on the system is 0. So therefore, from this you can see that when the moment becomes plastic moment, so the reactionary force acting at C will be MP of 4 MP over L. So this is the reactionary force acting at point C when the load reaches plastic load PL. Okay, so the reactionary force at A, then we try to find out. So because A is also a plastic hinge, so A also reaches fully plastic state. So the moment at this is plastic moment MP. So now we find out RA. So to find out the reactionary force acting at A, so we can apply now the sum of the forces acting on the system 0. So the first equation of equilibrium. So sum of the forces acting on the system is 0. So then we have the reactionary force A first here plus, okay, the force, this one, upward forces, we take it as positive. So we take upward forces as positive. So then this PL becomes negative. Okay, so some of the forces acting on this system will be 0. So then we can substitute our RC value here. Okay, we can substitute RC value. So because RA is from this you can write PL minus 4 MP over L. So then you can write moment due to C. So you can calculate what is RA from here. So from here RA will be PL minus 4 MP over L. So then we need to find out sum of the moments acting at C will be 0. So we apply sum of the moments acting at C is 0. So then the reactionary force RA multiplied by the total distance L minus the plastic moment at B, MP, then minus the moment due to the force here. Okay, so that is plus, okay, the moment due to PL into L by 4. So you get this expression for writing the sum of the moments acting at point C is 0. So we are not calculating moment due to the reactionary force C here, because we are equating the moments at C as 0. Then moment due to the reactionary force RA is RA into L. Then there is a plastic moment acting at point B, which is MP. So then the moment due to the load PL. So PL into this distance L by 4. Okay, so we can write this expression. So from this expression, then you can simplify. Okay, and you can see that the plastic load acting in this scenario is 20/3 MP over L. So we'll be substituting the values of RA from equation 2. Okay, so in this expression and simplify, then you will get the plastic load acting on this system, which is 20/3 plastic moment over the length. So in this scenario also, the plastic load decreases if the length increases. So that means if you want to have higher plastic loads, so you need to control the length L. All right, so this is how we'll be able to calculate the plastic loads acting on the systems. So when the load keeps on increasing to the maximum load or the plastic load, so where parts of the structure becomes fully plastic, and those parts are the points on the structure becomes first fully plastic, we call them as plastic hinges. And these plastic hinges we indicate with circles. And with the help of those plastic hinges, we'll be able to calculate the plastic loads. All right, guys. So I'll pause here for a while. Let me know if you have any doubts or any questions. All right, DJ says no. I'll be capturing your attendance now. I see. Kishan also says no. Can explain more on equation 3. Oh, all right, Daryl. Okay, so our aim is now we know the reactionary force at A and we know the reactionary force. We know these two things. Okay, so we know RA also in terms of the plastic load. Okay, plastic load means P subscript L. So when the load increases to plastic load, okay, the reactionary forces at A and C we could find out. So this is just by applying the equations of equilibrium. So now under this case, under this scenario, now we need to find an expression for PL, so the plastic load. So in terms of the plastic moments, so in terms of the plastic moments. So to calculate the plastic movements, plastic load in terms of the plastic movements. So now we apply on the structure on the free body diagram, the sum of moments acting at point C is 0. So this is the thing, sum of moments acting at point C will be 0 because the entire structure is in equilibrium. It is not in collapsing state. Okay. It collapses only when the entire structure becomes plastic. But the entire structure is not plastic only point B and point A is under plastic state, fully plastic. So under this, so you can increase the load up to this point where some points on the structure becomes fully plastic. So now the points which are fully plastic are A and B. Okay. So now with the plastic movements are developed at A and B. So now we know the reactionary forces at A and C. So when we sum the movements with respect to C is equal to 0, because still the equilibrium state is having. So we can write. So when you take the moments at C is equal to 0, so what is moment? Moment is the force multiplied by the perpendicular distance. So what is the moment due to RA? So we can write the moment due to RA is the force RA multiplied by the perpendicular distance to C. So because you're calculating moments with respect to C. So we can write RA into the length of the beam, that is L. Then we come, so the next moment here is the plastic moment at B. So there's a plastic moment at B is having here. Okay, so then you say plastic moment B, which is negative. Then the moment due to the reactionary force here. Oh, okay, sorry. The moment due to PL. So what is the moment due to PL at point C? So PL into the distance. So the distance is L over 4. So minus PL into L by 4. Because this is negative, because this is a downward force, and this causes movement, a downward movement. So here the movement is also negative. Okay. So both movement MP at point B and the movement due to the load PL at C will be negative. So this will be, we will be writing this expression, sum of the movements acting at point C is 0 when the beam is undergoing plastic load. So from this, we need to calculate only the plastic load. So we know RA, so you can replace RA value here. So then you can simplify this in terms of the plastic load. So you can simplify this in terms of the plastic load, and you can see the value will be 20 over 3 MP over L. Is that clear, Darren? All right. So then we move on to the your assignment questions. So the first assignment question here is that there's a continuous beam. So you can see here, it has a plastic moment MP. Okay. So when the moment reaches plastic moment, so you're asked to sketch the possible mode of failure and determine the magnitude of the load. So that means when this load increases to plastic load, PL. So where the plastic hinges are developed. So which part of the beam reaches the fully plastic state? Then, so you need to plot that structure, so the collapse mechanism, and find out the plastic movement in terms of the plastic load. So that means you find out what is the plastic load when parts of this structure of this beam, parts of the beam reaches fully plastic. So you can expect the plastic hinge developing here, and also a plastic hinge developing here. So, and you need to find out this plastic load. So in terms of the length here, so the only parameter here is length L, and of course the plastic moment MP. So when the load reaches to plastic load, so the movements developed at the plastic hinges are the plastic movements MP. Okay. So now let us see how the collapse mechanism looks like this. So the collapse mechanism, as you can see here, okay. So there will be a plastic hinge develops here. So this is a plastic hinge develops here, and there's a plastic hinge develops here, and you can see the beam, the L beam, so is pulled down. So when the load increases to plastic load, so here again the angular displacement theta is shown as very high. Okay, this is just for only description purpose. So the moment developed at the point B will be plastic moment MP here, and also at the point where the beam is connected is also the point A, right? So we'll have plastic moment. So the plastic hinges develops at point A and point B. Let me check here. So you can consider this as point A. So consider this as point B. Okay. So the plastic hinges develops at point A and point B. So that means the fully plastic conditions exist first at point A and point B. So when the load increases to plastic load, okay, so you can expect the beam to have a deformation. Okay, so instead of like this, so there may be a small deformation of the beam, and so the beam goes like this. All right, so this is, we call it as the angular displacement of the beam theta. Okay, so this is exactly the same thing is shown here. Okay, so just focus on this. I clear. Okay, so the two plastic hinges are important. Then the plastic movements you need to show. So the length of the beam here is L, here is L, and the load reaches to plastic load. So here theta is the angular displacement of the beam from its original state. All right. So here the question asks you to apply two methods. One is the equilibrium method, and the other one is the energy method. So what is energy, guys? So what is the concept of energy from your understanding, anyone? So what is energy? So we know equilibrium, the sum of the forces will be zero, sum of the movements acting on the system will be zero. So uh, yeah, any energy. So basically the concept of energy. So kinetic energy, potential energy are the different forms of energy, but basically energy is work done, right? So work and energy are the two sides of the same coin. So the energy is defined as the product of force and displacement. So if force is a vector, displacement is a vector, then you can say that the work done is the product of force and displacement. So work is energy. Okay, so when you do work, energy is created. When you have energy, then you have the capacity to do work. So work can be written as the product of the force and displacement. This is the dot product. So work is basically a scalar quantity. All right, so work is also energy. So if you have potential energy, then your force is the gravitational force mg. Okay, and the displacement will be your h. So since these two forces will be opposite to each other, therefore the potential energy will go as negative, because force and displacement will be opposite to each other when the force is the gravitational force. And in dynamics, you must also study that the work done is also equivalent to the change in kinetic energy. So the change in kinetic energy. So delta is change in kinetic energy. So that means the final kinetic energy minus initial kinetic energy. So work and energy are the same. So final KE minus initial kinetic energy. So that is the net work done. So final minus initial. So simply work done is the product of force and displacement. All right. So we need to find the plastic load by two methods. One is by the equilibrium method, the other one is the energy method. So the equilibrium method means we can apply the equations of equilibrium, that is the sum of the forces acting on the system is zero, and also sum of the moments acting on the system along x-axis is zero, and also sum of the moments acting on the system along y-axis also zero. All right, so we apply these two equations. Now, first, this is the collapse mechanism. Okay, so when you're asked to draw the collapse mechanism, you need to show something like this. Okay, so now first we apply the work energy method. So the work energy method. Okay, so when you apply the work energy method, so work is nothing but the product of force and displacement. So force and displacement. Now the force here is the plastic load. The load reaches plastic load. Okay, the load is PL here. The force is PL. The displacement here is this delta, the vertical displacement. So which is delta. So now you can uh, find an expression for this delta vertical displacement. So in terms of the angular displacement theta and also in terms of length L. Okay, so you can write the work done by the plastic load during plastic collapse of the beam is PL into delta. So this PL into delta, then we can apply the load is equivalent to the energy. So energy is, the work done is equivalent to energy. So what is the energy here? The rotational energy due to the plastic moment. So there are two plastic moments developed at A and B. So both will have the angular displacement theta. So you know that the energy due to a moment is movement multiplied by the angular displacement. So just like you can write F into S. Okay, so this is where the force is displacement is linear. Okay, so force and displacement, the energy or the work done. So the same force when it is replaced with the moment M, so then we need to replace the linear displacement with angular displacement M into theta. So the work done by the two moments will be MP into theta at point A and another plastic moment into theta at point B. Okay, so then you can apply the work energy theorem. So the work done is equivalent to the total energy of the system. Okay, so the work done is the force multiplied by the distance here. Okay, PL into delta. So this delta is the vertical displacement here, and theta is the angular displacement. So we can write PL into delta is equal to, which is the energy due to the force and linear displacement, then MP into theta plus MP into theta. That is the energy due to angular displacement. So you can add MP into theta, that will be 2 MP into theta. Okay, when the load is plastic load PL. So now we need to find the relationship between delta L and theta. So what is the relationship between theta? So from the figure here, so you can write theta is equal to, so if you refer this figure, okay, so you can write theta is equal to, anyone? So in terms of delta and L, so just focus on this triangle. So what will be the relationship between theta, delta, and L? So anyone, theta can be written as, no, this one you must have done many, many times. Oh, okay, tan theta can be written as L by delta, but when theta is small, you can simply write theta is equal to delta over L. Okay, delta over L. Or you can write delta can be replaced with L into theta. Okay, so this is, you must have done this in, S is the linear displacement, so you can write S is equal to R into theta. We have done this in vibrations also in your engineering dynamics, you must have done this. So V is R into omega. And A is R into alpha. Alpha is angular acceleration. So A is linear acceleration. Omega is angular velocity. So V is linear velocity. So theta is the linear angular displacement. S is the linear displacement. So R is the connecting factor. Okay. So here this R refers to the L here. Okay. So delta you can write L into theta from, as you write S is equal to R into theta. Okay, you can replace this theta with, sorry, delta with L into theta. So now find out an expression for PL, guys. I clear everything from here. Okay, so now your job is to find PL. So this is the guiding equation. So you can write PL into delta is equal to 2mp into theta. Okay, so you can replace delta with L into theta. So therefore, you can write PL, the plastic load, into L into theta is equal to, so you can write 2mp into theta, plastic moment into theta. So now you can cancel this angular displacement. So you can cancel out. So from this, plastic load can be written as, anyone? Yeah, that's right. So you can write 2mp over L. So you can write 2 by L into plastic moment. So this is the plastic load for this structure, okay, when the load increases to plastic load, okay. So this is, we have proved this by using work energy method. So the work energy method is work done, the total work done is equivalent to the energy in the system. Okay, now work done by the plastic load and work done by the plastic movement. So we are equating both the work done by the plastic load and also plastic movement. Then we'll be able to find an expression for plastic load. So in terms of plastic movement. Guys, any questions on this? Any doubts or anything, let me know. No questions? All right, so I clear this. So the next part of the question is you need to solve the same thing by applying the equilibrium method. So by applying the equilibrium method. So in equilibrium, you can just write the sum of the moments acting on the system will be 0. So this is one of the equations of equilibrium. So now here, what is the moment due to the load PL? So the moment due to the load is, you can write PL. The moment due to this is the force or the load multiplied by the perpendicular distance. So the perpendicular distance is L. So you can write the moment due to the load PL is PL into L. Then under these conditions, what are the two moments acting on the system? One is the plastic moment at A and the plastic moment at B. So some of these movements are 0. So when you consider the moment due to the load PL is positive, then the other two movements are negative. So you can write PL into L minus MP is equal to 0. So therefore, what will be PL? So you can write PL is equal into 2 by L into plastic moment. All right. So you can prove that PL is from both the energy method and equilibrium method. So you will be getting the same formula. Guys, any questions, any doubts? So this is the complete solution for this. Teaching says no. How about others? All right. So, guys, now at this point of time, I would like to tell you about your assignments. Number one, um, most of the assignments were not presented in a systematic manner. So now you need to go through the questions. Okay, what is question assignment for, let us say, milestone A? So each question try to write only on each page. So for example, if question 1 runs 3 or 4 pages, so you need to identify what is part A clearly and identify the final answer for part A. Then for part B, milestone A, what is the part B answers? Okay, and don't write on one page. Make 2 columns and don't write on 2 columns. So as far as possible, all the questions, part A, part B, everything must be written clearly, and if possible, do it, every part on a separate page, and always highlight your answer for the final answer. Okay. Otherwise, the first assignment I was a bit lenient in marking, but it was very trouble marking your assignments, mainly because you most of the assignments were not systematic. Okay, so you need to do it in a systematic way. So don't write the entire question in one page. So if you are doing so, means you are just writing from somewhere else. You are not working on your own. When you present your assignments, you must give the idea that you have worked out. It is not that you have written from somewhere else, or you are just writing. So there must be some description for each steps. All right, so take note of this to get full marks for assignment 2. So for assignment 2, there are many sketches required and these sketches need to be drawn clearly. All right, okay, I'll move on to the next question. Anything you want to give feedback, let me know. So you need to take more interest in writing your assignments. So clearly identify what is your milestone A, question 1, part A, what is your part B. So clearly, don't jumble up. And you can actually write in more number of pages and scan, your file size will not increase. All right, so take more precautions to when you are doing your assignment 2. So just to get full marks, and let me tell you, if you don't get good marks for the assignment, then end of examination, unlikely, you can score very high. It's going to be very challenging the end of term exam, even if it is online exam. All right, so considering that, work carefully your assignments. All right, so anything you want to convey? Any feedback? Let me know. I'll pause for a minute. All right, no. Okay, Gauri, thank you. Okay, so then we'll move on to online data. We'll move on to the question 2. These are incidentally the same questions for your assignment 2 also. So we can now, the question asks you, the beam has a plastic moment, MP. So that means the load is changed to the plastic load, PL. So when the load increases to plastic load, so there's a plastic moment. So you're asked to sketch the possible mode of failure, okay, and determine the magnitude of the force P for plastic collapse. So P means now when plastic movement, so the load P is PL, okay. So here you can see that this beam is pin connected here and also pin connected here. Okay, so here the height is h1, here the height is h2, the length here is L, and the load is acting horizontally. Okay, so when the load increases to plastic load, so guys, where do you expect the plastic hinges to develop? So where the plastic hinges will develop when the load increases to the plastic load. So here you can see that, okay, this is what is shown. So a bit of, I clear this. So initially the structure is like this. Okay, so the initial one I draw with, okay, so initial one, so before the collapse, the structure is like this. Okay, I just, so the purple color, okay, the blue color is before the collapse. So that means before the plastic load developed. Now here you can see that the beam is fully connected with a pin joint at both the bottoms. So there won't be any collapse at this point. Okay, uh, when when the load increases to plastic load, okay, when the load increases to plastic load, now the collapse mechanism looks okay. So the beam changes to okay. So the red one indicates when the load increases to plastic load. So when the load increases to plastic load PL, okay. So the plastic hinges develop at this point and at this point. Okay. So these two we consider as the, I clear this. So these two are the plastic hinges developed and the movements are plastic movements. Okay, so there is a angular displacement of the beam here that we call it as theta 1. Here the angular displacement is theta 2. Okay, so theta 1 and theta 2 will be different because the heights are different. So we need to find out geometrically, so the relationship between these angles and this h1 and h2. So that part you can see here. Okay, so we can follow the same thing, linking angular variables with linear variables. So theta 1 can be written as delta over h1. So delta is the linear displacement here. So delta in both cases will be the same. So the delta is the linear displacement of the beam. So we can say theta 1 is delta over h1. So similarly, we can say that theta 2 is delta over h2. So from this, you can write delta as h1 theta 1, and here delta as h2 theta 2. So that means you can relate this h1 theta 1 is equal to h2 theta 2. So from this, you can write theta 1 is equal to, okay, so this is the geometric relationship between theta 1 and theta 2. Or you can also write theta 2 is equal to h1 over h2 into theta 1. All right. So now from here, you need to apply the work energy theorem and also the equilibrium method to find out the plastic load PL. So what will be the plastic load PL? Okay, in terms of the plastic movements and in terms of the H1 and H2, the heights from the pin connector. All right, guys. So, can someone tell me what is the work done by the plastic load PL? Guys, I expect your response from you. So, work done by the plastic load PL. So, anyone? So work is nothing but the force multiplied by the perpendicular distance. You can only just say this PL. Then what will be the displacement caused by this PL? plastic load. Okay, so the displacement is delta here. Okay, both are delta. So the work done is simply PL into delta. So similarly, you can write down work done by the plastic movements. So can someone tell me what will be the work done by the plastic movements? So plastic movement multiplied by the angular displacement. So you can write it as plastic movement MP into theta1 plus plastic movement MP theta2. So there are two plastic movements developed and angular displacements are different. So we can write MP theta1 and plus MP theta2. Okay, so we know the relationship between theta1 and theta2 here. Okay, so you can probably write this as MP so theta1 plus, so I replace theta2 in terms of theta1. So instead of theta2, I write h1 over h2 theta1. Okay, and what is the relationship between delta and L and theta? So we can say that delta is equivalent to, so h1 theta1. Okay, we are done here. So you can write now work done by the plastic load and work done by the plastic movements will be the same. So PL into delta. So I write everything in terms of theta1. H1 delta is H1 theta1. So I can write H1 theta1. Okay, so here you can write theta1 multiplied by, so plastic moment MP plus, so here you can write H1 . Okay, so you can cancel out this theta1 theta1. Okay, so here you can write now this as MP into 1 plus H1 over H2. Okay, so our aim is to write the plastic load. So you can write PL is equal to, okay, so you can simplify this. So you, okay, simplify and write down your answer. So that will be the work energy method. Is that clear, guys? Any questions? So this will be your collapse mechanism. So you can write, you need to show your collapse mechanism also. You need to show clearly the PL, the delta, the theta1, theta2, then the plastic hinges and the plastic movements, the MP. So when you do your assignment questions, or the sketch must be clear and you need to show everything, and all the steps must be written systematically. So any missing steps, the marks will be deducted. All right, any doubt or anything you want to ask about this? So someone must respond. I see. Vichen says no. How about us? Okay, so everything says no. All right, we know. Okay. All right. So now the same thing you need to work out using uh, the equilibrium method. So equilibrium method means you need to apply the sum of moments to zero and sum of forces acting on the system to zero. So when you want to do this equilibrium method, sum of moments to zero and sum of forces to zero, okay, the net force acting on the system will be zero. So we can see the first one, okay. So call the pin joints as A and B. So just take part of the structure. When the load is P, okay, when the force is P, so there is a equal and opposite force at point A. You can call it as FA. So similarly at the another pin joint, so the force is for P, the applied force is P, then the reactionary force at B will be, you can say FB. Okay, so the moment is plastic moment here, and also the moment is plastic moment here. So this is the free body diagram you can visualize. Okay, so when you apply the at point A, take the first point. So at here, so point A refers to this one. Okay, so apply sum of moments at A is zero. So the moment due to the force A will be force A into H1, then the plastic moment acting on the system. Okay, so this is the plastic moment. So you can write FA into H1 minus plastic moment is equal to zero. Okay, so that means the force A can be written as plastic moment over H1. So similarly at point B, so you can write some of the moments acting at point B is zero, then you can write force acting at point B will be the plastic moment over H2. Okay, so during the plastic collapse, okay, so the total force, the plastic load is equivalent to the force at A plus force at B, because both point A and point B are connected. So therefore, the plastic load is the sum of the two reactionary forces, FA and FB. So just substitute FA, FB and calculate, you will get the plastic load. And whatever the answer you get here will be the same as you got it for the um, previous work energy method. So for both the methods, you will be getting the similar answer. Is that clear, guys? Any doubts? Let me know. All right, so you can complete the working. Then here also you can complete the working, and you can show the final plastic load by both the methods will be the same. So now let us look at the next question. So there are only 3 questions under plastic design. So for all the 3 questions, you need to draw the collapse mechanism, and also you need to find out the plastic load in terms of the plastic movements and in terms of the geometrical parameters of the structure. In most of the cases, it will be the length of the beam. So in this question, there are 2 loads acting P. So the geometry is shown. So the beam is supported at point A, supported at point, okay, let us say you have 3 supports here. One is the pin joint here, then this is a roller supporter, and this is also a roller supporter. So it rests on 3 simple supports and is subjected to 2 equal concentrated loads indicated. So these are the 2 concentrated loads. So you're asked to determine the magnitude of these loads for plastic collapse of the beam. So you're asked to use both equilibrium and energy methods here. Okay, so we can use the work and energy method here. So you need to first draw the collapse mechanism. So collapse mechanism, you can basically visualize if you see the deflection curve. So the deflection curve may simply so the maximum deflection will occur exactly where the load is concentrate acting. Okay, so it goes to this, and again from here. So I'm just drawing the deflection curve. So of course the drawing is highly exaggerated amount of deflection. So it will be like this. So this will be the how the beam will get deflected at the 2 loads when the load is increased to the plastic load. Okay, so you can see and just okay, there is an example related to this type of question in the letting guide, so you guys can also look that. Okay. So there will be a plastic hinge here. So there will be a plastic hinge here. Okay, and of course there will be a plastic hinge here. Okay, so can someone tell me what will be the angle here? So if this is the angle theta, so if this is the angle theta, so this angle will be, so this will be 2 theta. So similarly, the angle is theta here, angle is theta here. So this angle will be 2 theta. Okay. So there is a plastic moment here. So there will be a plastic moment here. Okay. And there will be a plastic moment here. So because the beam is getting deflected at all these points, so there will be plastic movements at all these points. So plastic hinges. So plastic hinges represented where the movement is plastic movement MP. So these are the 3 points where you can expect the beam reaches fully plastic conditions, okay, under fully plastic conditions. So here the moment is MP. So here the moment is MP. So here the moment is MP. So we can apply the load is PL here. So the displacement here. So I just represent. So you can consider this is the vertical displacement delta. Okay. So this is the vertical displacement delta. Okay. So the total work done by these two loads, so you can write PL into delta plus PL into delta. So the work done by the plastic loads. So the total work done will be 2 PL into delta. Okay, so now we need to equate this work done by the plastic loads. So with the work done by the plastic moments. So in all the cases, you can see the angular displacement is theta, but the moment due to the plastic load MP here will be, so MP into 2 theta. So we can write 2 PL into delta is equal to, so the work done by the plastic moment at this point, you can write MP into not theta, but the angle is 2 theta. So you can write 2 theta. Okay. So here the moment due to the work done due to the moment MP will be, so you can write MP into theta plus MP into theta. So one side it is theta, the other side is also it is theta. So you can write MP into theta plus the moment due to the work done due to the moment at this point is, again you can write MP into 2 theta. So here the angular displacement is 2 times theta. Okay, so now you can add up these things. So you can write this will be 6 MP into theta. Okay, again you can replace delta in this case. Okay, so delta will be, so in this case theta L over 2. Okay, so delta is theta L over 2. So you can write, so 2 PL, okay, theta L over 2. Theta L over 2. So you can cancel this 2. Then from here you can write down what is the plastic load in terms of plastic moment. So you can cancel out theta. So you can write this plastic load as 6 over L plastic moment MP. Okay, so 6 over L here. All right, so this is how you can draw the collapse mechanism, and you can apply the work energy equation here. Guys, any questions? All right, Deacon, how about others? And how about others? Anybody else? Takashi says no. All right. Okay, Shafiq, good. So I clear this. Oh, I'm sorry. Okay, I clear this. The next part, you need to do the analysis for the equilibrium method. Okay, so we have done the work energy method, then carry out the same thing for the equilibrium method. Okay, so this is the same figure which I have drawn. So you can just use the same figure to calculate uh, the plastic load using equilibrium method. So you can do sum of the forces equal to zero, or then you can apply the sum of moments acting on the system will be zero. Then you should be able to get the same answer as we derived for the part A. All right. So that part I'll leave it to you. All right. So with that, we complete this plastic design part. So under plastic conditions, so we have seen the plastic flow rules to begin with, so followed by the plastic bending, so followed by the plastic design. So every part, I think there will be a question from for the end of term exam. So plastic analysis is important. So elastic stress strain relationship is straightforward, but when the material enters into plastic deformation, so you need to understand the plastic flow rules and the safe yield calculation, yield stress calculations. So followed by the plastic bending, so how you can establish the neutral axis, then how you can calculate the plastic movements and elastic movements and the residual stresses. So then the last part is the plastic design. So where you calculate the plastic load. So when the plastic hinges are developed on the structure. All right. So after this, then we move on to the next topic. So I'll give you a break at 8:30. So we can have break at 8:30. Okay, so the next topic is the buckling of columns. So buckling of columns is not bending of beams. So beams are horizontal structures. So the columns are vertical structure, right? So a column is nothing but a long, slender members. So here they are subjected to axial compressive stresses, so compressive forces, or it could be elongating forces. So this is a column. So the failure of the column is subjected to a load P. When the load keeps increasing and reaches a critical value, so the column gets deflection. So here the deflection is lateral deflection. So this lateral deflection we refer to the buckling of columns. So when the load exceeds to a critical load, okay, when P increases a critical load, so then the column will deflect laterally. And here the idea is to calculate what will be the critical load in terms of the, the geometrical parameters of the column and in terms of the um, load applied and where the load applied. Okay, so the critical load refers to the maximum axial load on a column. So when the column is on the verge of buckling, so when the column is on the verge of buckling. So theoretically, we can prove that when we are dealing with a column, so here which is pin supported, okay? So the critical load can be given as pi square Young's modulus, then I refers to the inertia, mass moment of inertia of the column. L is the unsupported length of the pin end column. So we'll slightly modify this equation a bit later. So we can say that the critical load is equal to pi square EI over L square. But how the length is defined, that is important. So in this formula, L represents unsupported length of the pin end columns. Okay, so we can also calculate the critical stress at which, so when the load is critical, so the column experiences a stress, that stress we call it as the critical stress. Okay, so critical stress is nothing but the critical force over critical load over area. So if you take those two things and simplify, so the critical load can be given by this formula, pi square E. E is the Young's modulus. So L is the length again. Then R is the radius of gyration. So R is the radius of gyration, and R can be calculated as the moment of inertia I over the cross-sectional area A. So I over A. Okay. So R is the radius of gyration. So this is the critical stress acting on the column when the column is about to collapse. So this L over R is also known as this slenderness ratio. So this ratio is a measure of column's flexibility. So, and we'll be using this slenderness ratio to actually classify columns, okay, as long, intermediate, and short. Okay, the next slide, okay, we define for buckling of columns, so we define effective length. So effective length is the length if a column is not supported by pinned ends, okay, there's a formula to find out this effective length. You can see this is the important slide here. So the effective length is defined in terms of how the column is supported. So when the column is supported at both ends, okay, at both ends by pinned. So when both the columns are pin connected, then the effective length L is equivalent to the given length. Okay, so in this case, the ratio, this K is L over LE, so which is 1. So when the column is connected by pin both ends, then the effective length is the original length of the column. L is equal to LE. But when the column is fixed at one end, okay, here the column is fixed and is free at the other end. So in this case, the effective length is 2 times the original length. So the effective length is 2 times the original length when we have a scenario the one end is fixed, the other end is free. Okay, so when we have both ends are fixed, so the bottom is fixed, the top is fixed. So in this case, the effective length is half of the original length. So the effective length is only half of the original length. So in the last scenario where the one end is pinned and fixed, okay, one end is pinned, the other end is fixed. So in this case, the effective length is 0.7 times the original length. Okay, so this is how we can find the effective length when the column is supported by different types of supports. So the straightforward, when both the ends are pin supported, the effective length is equivalent to the original length. Okay, if it is fixed at one end and free at another end, the effective length is 2 times the original length. So if you have both ends fixed, the effective length is half of the original length. So only these 4 scenarios we have. If one end is pinned and the other end is fixed, the effective length is 0.7 times L. So when you're dealing with a problem and based on the description of the problem, then we can find out the relationship between the effective length and the given length. So only these 4 alternatives we can visualize. Okay, so when we describe the lengths in terms of effective lengths, okay, so we can use now the critical length formula. So P critical, okay, this is the critical load at which the column buckles, is pi square into EI. E is the Young's modulus or the modulus of elasticity. I is the mass moment of inertia of the beam. K is the slenderness ratio. Okay, instead of KL, you can simply use effective length also. Okay, LE square. So the K value you can define whether K is 1 or K is 2 or K is 0.5 or K is 0.7 depending on how the column is supported. Okay, so K value you can use, otherwise you can just write effective length. Then the critical stress formula can be just given as KL over R whole square, pi square E over this much. So these 2 formulas will tell us the critical load and critical stress when the column is about to buckle. Okay, the load required is critical load, and the stress at that point is the critical stress. So these 2 equations we'll be using to calculate the critical load and the critical stress for buckling of columns. So this KL by R is known as the effective slenderness ratio. Okay, so when you calculate, when the load is acting exactly at the centroid of the beam's cross section. So now if you see in all these cases, the load is acting exactly at the centroid of the column, okay, at the center of the column structure. But when the load is not acting at the centroid, but it is acting away from the centroid. Now you can see here, okay, you may just focus okay, so you can see here the load is acting not at the centroid of the cross section, but it is acting at a distance away from its centroid. So this E is called the eccentricity. So when the load is not acting at the centroid of the cross section, but away from its, okay, by an eccentricity or by a distance C, so then the load acting, the critical load calculations will be done by using what's known as a secant formula. So secant formula is used to calculate the critical loads. So when the load is acting away from the centroid of the cross section, where you need to know the eccentricity E. So where the load is acting on the column. So there is no requirement that always the load is acting exactly at the centroid of the cross section. So when the load is acting away from the centroid by an eccentricity E, okay, then we use the secant formula to calculate the critical load. So I will just go to the final formula that is most important. So here, this is the maximum deflection you can calculate using this formula. So the maximum deflection due to a load P. So P is the load. This load is acting at an eccentricity E. Okay, so where the length is L, let us say. So we can use the maximum deflection caused by the load. When the load is acting at an eccentricity, you can use this formula to calculate the maximum deflections. Okay, so this is the formula for maximum deflection. So here the angle referred here is secant, so inverse of cosine. So secant theta is inverse of cosine theta. Now to calculate the maximum deflection, so the secant formula, you can just prove that secant formula. This is the secant formula. Let me see. Yeah. Okay, so the secant formula is the most important formula under buckling of columns. So where you calculate the maximum elastic stress developed in the column due to a load P applied at an eccentricity E. Okay, so when E is equal to 0, then you will have critical load. So you can use critical load formula. So there is no need to use secant formula. Okay, so secant formula applies where there is an eccentricity when the load is applied away from its neutral axis. So P over A refers to the cross-sectional area of the column. So 1 plus EC over R square. So E is the eccentricity. So it is the distance from neutral axis to where the load is applied. So C is a geometric parameter. So with reference to neutral axis, the farthest point on the cross section. Okay, so you know the same concept of buckling of columns when you bending of beams we have done, the Flexner's formula, the same meaning for C. Over R square into secant L over 2R. So here L refers to effective length. Okay, so P is the load applied, E is the Young's modulus. So R is the radius of gyration, so which we have seen R is equal to square root of I over A. Okay, so you can see R is square root of I over A. So I is the mass moment of inertia, A is the cross-sectional area of the column. So C is the distance from neutral axis to the farthest distance on the cross-section. Okay, so for example, if you have a T-beam like this, let us say, so you have a T-beam like this, and let us say neutral axis is here. Okay, now with reference to neutral axis, the farthest point on the cross section. So this will be your C. Okay, so C represents distance from neutral axis to the farthest point on the structure. So A is the cross-sectional area. L is the unsupported length. So basically, when you are doing for non-pin supported columns, so we'll be using the effective length in the formula. So this length is always, make sure it is LE, effective length. So this becomes only L when you are dealing with both ends are pin connected. Otherwise, we have to use the effective length. Okay, so that's why you can always keep this formula as LE, and you change LE is equal to L if the description of the problem gives you that both ends are pin connected. All right, so this is the secant formula which will be used to calculate the maximum stress acting on the cross section when the load is applied P at an eccentricity of E. Guys, can you tell from this formula how many unknowns are there? Okay, so E and C are basically the geometric factors depending on their given geometry and also the L length. Okay, R is also basically a geometric factor which is square root of I over A. So I is the mass moment of inertia. So you can say I is also a geometric factor. Okay, so then R, okay, A is the area, of course, it's a geometric factor. So that leaves us only two things. E is the property of materials, Young's modulus. So this is never a parameter to be evaluated from this equation. So that leaves there are only two things to evaluate. One is if you know the load acting P, then you can calculate the maximum stress due to the load P. Or if you know the maximum stress, then you can calculate the load bearing capacity of the column, that is the P. So we use secant formula to either calculate P or the maximum stress sigma max. So in rare cases, we may be using to calculate, this is for design related estimation. So you can calculate the length of beam required. So if you know the maximum stress and if you know the maximum load acting on the column. Okay, so this is the secant formula to calculate the maximum stress acting on a column when the column is acted upon by a load P, okay, away from the neutral axis at an eccentricity E. All right, so this formula, there are two important things. One is if you know load, you can calculate the maximum stress, or if you know what is the allowable maximum allowable stress, then you can calculate what should be the maximum load acting on the column. All right, guys, any questions? Let me know, or anything you want to ask about the buckling of columns. So I just go back from the beginning. Okay, so the first thing in this buckling of columns is, so where you can calculate the critical load. Okay, okay, so the critical load you can use the critical stress acting on a column, okay, to buckle. So you can use these formulas to calculate. Okay, so K is basically, you can understand from the description of the effective length, how the column is connected. So based on that, you can use this formula to find out at what critical loads the column can buckle. Okay, otherwise you can also calculate at what will be the critical stress acting when the column is about to buckle. Okay. So here both these equations are useful only when the load is acting exactly at the mass center of the column's cross-sectional area. If the load is not acting on the cross-sectional area but away from its cross-sectional area, then we need to apply the secant formula. So there are two types of secant formula. One is the calculating the maximum deflection. Okay, so we can use this formula to calculate the maximum deflection due to the load P when it is acting at an eccentricity of E. Okay, so much more important than this is the secant formula to calculate the maximum stress acting on the columns area. Okay, so this is where you can see Okay, so the maximum stress is related to the load applied and eccentricity ratio here and the length, okay, everything. Now, this equation is a bit specific in the sense, so here you can see the load P is coming out as a product and also it is inside the product. Okay, so the load is acting at in the formula you can see as a product and also within the product. So therefore, it is not possible to rewrite this formula in terms of P. You cannot separate out the P and you can write an expression P in terms of the other parameters. So mathematically, we cannot separate out P from this formula. Okay, so the maximum stress is written in terms of the load applied. Okay, but if you want to calculate P, if you know, let us say is sigma max, the maximum stress acting on the column, if you know, you cannot evaluate from this formula mathematically the load P. So if you want to evaluate, then you need to use a method what is known as the trial and error method. Okay, we'll see about that trial and error method during our calculations. So in buckling of columns, again, end of term, will be a question in the exams. So most of the time you may be using the secant formula. Okay, so there are two secant formulas. One is to find out the maximum stress and the other one is to find out the maximum deflection. So we use secant formula when the load is acting away from the neutral axis on the column. Okay, so E is the eccentricity. If the load is acting exactly at this neutral axis, then we can calculate the critical load or the critical stress easily from this formula. All right. So, guys, any questions? Please, I would like to remind you that this Sunday you will be taking your mechanics vibration online class test. So the class test will be between 3 to 4:30 p.m. So 3 p.m. to 4:30 p.m. So this is just to remind you that not like solid mechanics you are doing in the evening, but you'll be doing in the afternoon, 3 p.m. to 4:30. We'll discuss tomorrow. All right. Yeah. So we'll be discussing tomorrow. There will be 4 questions, of course. We can discuss a bit more in tomorrow's session. Okay, so now the time is nearing 8:30. So let's go for a break and meet again at. So we'll meet at 8:50. Is that okay? All right. So we'll meet at 8:50. I'll be back at 8:50. Hi guys, hope you're all back. All right, Shashwin, and how about others? All right, Jian. Oh, Michael, okay. How about others? All right, Safaruddin. Elong, okay. All right, Noor. Azhar. All right, so let us go through the first question here. So the first question says pivot ended. So the description is pivot ended. So that means the L is effective length. So that means K is 1. So the diameter of the steel bar is given 30 mm. So if you know the diameter, that means you know that you can calculate area. And the length is given. So it is used to support a compressive load. So a factor of safety is 2.0 is specified, and the eccentricity ratio is given as 0.30. So eccentricity ratio means EC over R square. So this is the eccentricity ratio. So this is given as 0.3. Only eccentricity means E. If it says eccentricity ratio, so that means you are looking at EC over R square. So you know R is the radius of gyration, which is square root of I over A. Okay, so the parameters are given. The yield stress is given 300 megapascals. So the Poisson's ratio is given as 200 gigapascals. So now you're asked to determine the maximum safe compressive load and implied value of eccentricity. So implied value of eccentricity means you are asked to calculate E. Okay, and the value EC over R square is given. So calculating E simply requires you to calculate okay, R and C. Okay, so C in this case will be uh, because the cross section is diameter, so C will be half of the diameter. So from the neutral axis, the maximum distance on the cross section will be half of the diameter. So C will be 15 mm. All right. So then you can calculate R. So then use from this formula, you can easily calculate eccentricity value. But before that, you need to calculate the maximum safe yield compressive load. So you have to calculate the P safe. So what compressive load you can use safely. So when your factor of safety is 2.0. All right, so the question is now to calculate the safe field. And since you're dealing with eccentricity, so we need to use the secant formula. Okay, so here we can see, first calculate the area, guys, and let me know. So this is a solid steel bar. So what will be the area? So you can use pi d square by 4 or pi r square by 2. So can you calculate and let me know a value, area? So I'll be waiting for your answer. Uh, 7.069 into that's okay. Then you can calculate the mass moment of inertia. So mass moment of inertia is a geometric property since you're dealing with a steel bar having a diameter, so circular cross section. So the formula for the mass moment of inertia for a circular cross section is pi r to the power of 4 over 4. So this one you can refer the geometric properties and you can look for the inertia formula. So you can calculate r, is the radius. Yeah, so that's correct, teacher. So then you can calculate the radius of gyration or so which is I over A. So the values are shown. You can just calculate the ratio. Michael says 7.502. So what is that 7.502? Is that R? Okay. So what is the unit? So you will get 7.5 mm. So you can write either 0.0075 meters or 7.5 mm. No, that's correct, Michael. So once you calculate these things, then we look at the secant formula. So the secant formula is just copied. So the maximum stress is P over A into 1 plus EC over R square. So this is the eccentric ratio. The value of this is given 0.3. Okay, I start recording. I got. Okay, so we know the eccentricity ratio. Then we know that the length L is equal to effective length is equal to 1. So now we can use the secant formula, and the maximum stress is given as the yield stress is given as 300 megapascals. Okay, so sigma max is given as 300 megapascals. So we know sigma max, we know area, we know AC over R square, we know L, we know 2R, we know EA. So the only unknown is now you need to calculate P, the safe load. Okay, so the formula is sigma y is I'll just go back to the formula. Okay, so you can see sigma max is P by A. This is the formula, right? So, and now the question says that a factor of safety of 2.0 is specified. So because of the factor of safety is 2.0, so, and also the safety factor is 2.0 given. Okay, so to maintain the safety factor of 2.0, so we reduce the stress by 2. So the as sigma max, now we can take it only as 300 over 2. Given the safety factor as 2.0, so we can take the maximum stress as 300 over 2.0. So that is, we take the maximum stress as 150 megapascals. So now you substitute 150 into 10 power 6. So P over A, so you can write down the value of A also. Then 1 plus 0.3, EC over R square is 0.3. Okay, then secant, so 1 over 2R, so you know the value of R. Then P we need to calculate, Young's modulus E is given, then you know A. So substitute everything into the equation. Okay, then okay, this is, you cannot solve uniquely P value, because P value is a factor of product, and also it is coming as within the product. I'm sorry, I clear. So you can see the whole thing is in as a product of P by A. At the same time, within the product you have P. So there is no way we can separate out this P in the calculation. So therefore, what we do, we follow the method known as the trial and error. Okay, so we simplify this equation, and you just multiply, cross multiply with a, and then appropriately reduce this equation. Probably you may end up getting something like this. So you may, okay, once you put everything and simplify, so you may be able to get something like this. So right hand side you have 106050. Then the left hand side you have p into 1 plus 0.3. So the secant, within the secant you have so much. Okay, so now you need to choose appropriate values for p. Okay, so choose some estimated values for p and calculate and compare with your right hand side. Okay, so you need to choose an appropriate value for p and then calculate this, evaluate this equation and compare with your right hand side. So depending on the value comparison, depending on whether your calculated value for this equation is less or more than this, then again you can revise the p value and recalculate. Okay, so this way you have to do 2 or 3 iterations, and once you do that, then you will be able to find out a more suitable value. Okay, uh, this is only by trial and error. So that means you need to pick up a p-value which will give you, once you do the calculation, a value very close to 106050. Okay, as an initial approximation, so you can you can estimate that the maximum value for any trigonometric angle is 1, right? Sine 90 is 1 or cos 0 is 1. So the maximum value for this can be 1. So when you consider the maximum value for the whole thing as 1, so then you can simplify this as 1.03 into p. So that means p value can be approximately 106050 over 1.3. This is an approximate value, not the exact value. So you can start estimating this expression. So considering a p-value of so much, then calculate the entire thing and whether check you are getting very close to 106050 or not. So if not, you can just modify this value and then recalculate and compare again. So after 2-3 iterations, then you can fix one value so that you can take it as answer for your the load P. Guys, is that clear? So you need to do 2 or 3 iterations, so starting from an approximate value like this. Okay, so sometimes if you use the same value, you may get very close to this. Then you can fix this value as the answer for P. Okay, so there is no unique way of solving this, but only by trial and error. So starting with an approximate value for P as 81577 newtons, then you estimate this expression. So estimate this value. So from that estimation, whatever the value, you compare with this right-hand side value. So if you get lower, then increase p-value. If you get higher, then decrease p-value. Then recalculate and compare. So after 2-3 iterations, then you can fix your final answer. So therefore, your final answer will be an approximate value, but not exact value. So is that clear? Guys, any questions on this calculation? How do you know which one is the final answer? The one which is closer to your right-hand side. So the one which is closer to the right hand side. So how to find it? You have to do 2 or 3 times. So secant, you can use your calculator. So in secant theta is inverse of cosine theta. So secant theta is 1 over cos theta. Don't try to do the calculation now, it may take a bit longer. So I'm just avoiding you the calculation part. Okay. Do we need to show all the estimate that we do? At least 2 or 3 iterations. So 2 or 3 iterations or 2 or 3 calculations. All right. So you will get a final value. So most likely you will be getting very close to this value. May not be exact, but very close to this. All right. The next part of that is calculating the eccentricity. So we know that EC over R square is given as 0.3. Okay. So then we know C is 15 mm. That is 0.015 meters. Then you calculated R, so then take R square. Okay, then you will be able to do or get the value of eccentricity. So can you calculate and find what will be the eccentricity? That's correct, Michael. So what is the unit? 0.001125. So I think your final answer will be 1.125 into 10 power 3 meters. I think you're putting one extra zero. All right. So I clear this, then we'll move on to the next question. So this question is a direct application of the secant formula. So the calculation is based on the trial and error method. Otherwise, all the given data is available in the form, in the description. Okay, next question is similar to your assignment question. So here is steel bar AB. So AB is the steel bar. So this is A, this is B. So the steel bar, the length is 6 meters. So both are pin connected. So the frame is pin connected at its end. So that means the L is the effective length is 6 meters. So determine the factor of safety with respect to buckling about the YY axis. So here the buckling is along the vertical axis due to the applied loading. So we need to, so where is the loading? So the loading given is only horizontal loading, you can see. So there's a horizontal force acting here. so which is 18 kilonewtons. Okay, so the dimensions of the mechanism is given. So we have this is okay. The vertical distance is 4. The horizontal distance is 3. Okay, the properties: the Young's modulus 200 gigapascals, and the yield stress is at 500 megapascals. Okay, so this is the data given. So what you need to calculate, you have to calculate the factor of safety with respect to buckling along the YY axis. Okay, to do this, you need to first draw the free body diagram. Okay, the free body diagram you can see. This is the horizontal force acting on the system. Okay, so due to this, there will be a vertical force. So you can see the vertical force is acting like this. Okay, and AC is connected with a link again. So the force AC will be like this. Okay, so this is C, this is B. Let us say AB. Okay, so this force is given horizontal force 18 kilonewtons. So now to find out what will be the force FAB. This is the load acting on the steel bar AB. So we need to calculate the load acting on AB. Okay, so you can see okay, so from this triangle, so you can see this is the angle theta. Okay, so from here you can write, so what will be sine theta? So if this is 3, this is 4, this will be 5. So sine theta is the vertical. Okay, so 4, okay, angle is this, so this is your 90 degrees. So sine theta will be 3 by 5. So cos theta will be 4 by 5. So this is just to find out what is the force acting AB. Okay, so you know the horizontal component of the force FAB sine theta. Okay, so you can write the horizontal component of this force. Okay, you can write it as FAB into sine theta is equal to 18 kilonewtons. Okay, so then you can calculate the force acting along AB. So you are resolving the force AB, the x component. Okay, the acting along the horizontal is FAB into sine theta. I think just hold on a minute. This will not be FAB. So we are taking the horizontal component of FC. So FC into sine theta. So FC into sine theta is like this. So this will be FC into sine theta. So the horizontal component of FC, okay, sine theta, we are equating to 18 kilonewtons. So therefore, you will get FC. Any answer for FC, guys? That's correct, Michael. So FC, you get 30 kilonewtons. Then we are more interested to find out the force acting along the steel bar AB. So how to find out force acting along AB? So for this, FAB will be, so you can write FC into cos theta. So the vertical component of this will be FAB. So you can calculate FAB. How much will be? So FC is 30, cos theta is 4 by 5. So 30 into 4, 120, 120 over 5. So that will give you 24 kilonewtons. So this is the force acting vertically on the steel bar AB. Guys, is that clear? So the force or the load is acting vertically along the YY axis. So therefore, you can calculate the critical load. So what will be the critical load? So critical load for the buckling. So you can use the formula pi square EI over effective length square. So you can calculate the critical load. So to calculate this, you need to know inertia, I. So to calculate inertia, it is a steel bar. So we know the length. So the inertia for this is 1 over 12 because you are looking along the YY axis. So inertia through the neutral axis is BHQ. So the cross section is shown here. So we use the cross section to calculate inertia along YY. Okay, so you will be able to estimate P critical. So once you know P critical, then you can calculate the safety factor. So the safety factor SF will be, so your P critical. So that means the load at which the column buckles over the load acting on the steel bar, that is the force AB. Okay, so if you do these calculations, so you'll be able to get the safety factor. So guys, I'll pause here for a while. Any questions, let me know. Otherwise, I'll move to the next question. So somebody must respond. All right, so this is actually all the working is shown here. So safety factor, you can just calculate from here. All right, so I clear this. We'll go to the next question. Okay, so let us look at this question. So here, an aluminum hollow box column of square cross section. So the cross section is given as a square cross section. Is fixed at the base. So the base is fixed and free at the top. So when the base is fixed and free at the top, so the effective length is 2 times the original length. So from the description, we know that now because it is fixed at one end and free at another end, the effective length is 2 times the original length. Okay, the dimensions of the box is given. The width is 150 mm, the thickness is 10 mm. So the box is, the dimensions are given 150 multiplied by 10. Thickness is 10. Okay, so this is a square box. So square cross section. A compressive load of P160 kilonewtons so acts on the outer edge of the column, okay, at the midpoint of the side. So it is, load is acting at the outer edge of the column at the midpoint of the side. So somewhere the load is acting okay, so the load is acting something like this. So the load is acting at the outer edge of the column at the midpoint of the side. So at the midpoint of the side. Now, what is the longest permissible length L of the column if the stress is not to exceed 100 megapascals? So here what is given, the stress is given not to exceed 100 megapascals. So sigma max is given as 100 megapascals. So there is no safety factor involved. So therefore, we can use the sigma max as 100 megapascals. So here, the load is not acting at the centroid of the cross section. So therefore, we need to use the secant formula. We need to use the secant formula. So first things first. So can you calculate the uh, section properties? So section properties calculate. First, let me know what will be the area A. Can someone calculate and let me know? So it is a hollow box of columns. Okay, square cross section. So I'll wait for your answer for A. Okay. So any of the calculations are shown here. So area is the, you need to calculate the outer area square minus the inner area. So can you do this calculation, because you are dealing with a hollow box of square column. So area represents only the outer area minus inner area. Addition correct. So you get 5.6, that's right, into 10 power minus 3 unit. Yeah, that's right, meter square. So 10 power minus 3 meters square, or you can also write 0.0056. Okay, then the effective length is 2 times the length. Okay, so the maximum compressive stress is given 100 megapascals. So then you need to calculate the inertia of the uh, square hollow box. So for the inertia for the square, the formula is 1 over 12. So width to the power of 4. So this is the formula for the inertia for the hollow box, square box rather. So over here you get, okay, so 1 over 12, okay, outer width, that is 150 mm to the power of 4, minus inner is hollow, so 0.13, thickness is 0.1, so you need to subtract 0.13 to the power of 4 over 12. So you can use this formula to calculate. So inertia is 1 over 12, b to the power of 4. So can you calculate and let me know how much you get? So tell me what is the inertia value you have calculated. No result is giving me 1.84 into 10 power minus 5. The unit, okay, so the unit is meter to the power of 4. No result, I think your calculation is correct. So 1.84 into 10 power minus 5. So then you can calculate the radius of gyration. So I over a square root. So I think you will get 0.0573. So we can calculate the radius of gyration. So what will be the eccentricity value for this? Anyone? So can someone give me the value for eccentricity? So this is the eccentricity value. So can you let me know how much is your answer? Uh, 75 means half. 75 refers to from here to here. So that is the C. 0.065 refers to here. So the problem says that the load is acting on the outer edge of the column at the midpoint of the side. So Dichen, can you revise your value? Yeah, that's right. So eccentricity, you can take it as 0.07. Okay, so where the load is acting with respect to the neutral axis. Whereas the C is simply from the neutral axis to the farthest point on the cross section, so which will be just B by 2. So B is 15 mm, therefore C will be half of that. Then use secant formula. So now use secant formula, you know, for sigma max, you know, given 100 megapascals, right? So you know sigma max. So the load is known, right? So the load is acting 160 kilonewtons. So P is given 160 kilonewtons. Okay. So E, you know, C, you know, R, you know, so you know everything. EC over R square. Okay. So eccentricity, you know, 2R, you know, so the whole thing, you know. So the only unknown quantity is L. So use L as effective length. So you, instead of using LE, so use 2L. Okay. So since you know everything, you will be able to estimate 2L. Okay. So from there, you can calculate the effect length L. So this is for designing the beam. So this will be the longest permissible length of the column. Is that clear, guys? So you need to evaluate this calculation. Okay, the calculation takes some time because the secant theta is involved. So you will get the answer in radians, then convert the radians into degrees. Then you can calculate the length in meters. So let me know if you have any questions. How do we get 0.07? All right. No, 0.07 refers to the eccentricity. So eccentricity means from neutral axis where the load is acting. So from the description of the problem, the load is acting on the outer edge of the column at the midpoint of the side. So if you take this is the thickness, okay, of the side. So it is acting at the center of this. Okay. So from neutral axis, the whole breadth is 15 mm, right? Okay, it is given as 15 mm. So from neutral axis passes through exactly at the center of the hollow rectangle. So that means from one end to the neutral axis is 0.75. But since the load is acting at the midpoint of this thickness, okay, so the thickness is given as how many mm? Okay, width is 150 mm, thickness is 10 mm. So that means this is acting 5 mm from the edge at the center. Okay, so half of 150 is 75. So 75 minus 5 mm. So that gives you 70 mm. Is that clear? Okay, so this is how you get 70 mm. All right, so final calculation you can do. Any other questions? So you'll be calculating the longest permissible length L under the maximum stress of 100 megapascals, and when the load acting is 160 kilonewtons at the given eccentricity, and it's a hollow box. All right, guys. How about others? Any other questions? Let me know. So before we move on to the last topic, Daryl says no questions. How about others? So I clear this everything. So someone must respond before I move on to the next topic. All right, Mr. Dicheng Takashi. All right, then we move on to the last topic. So the last topic is about thick wall cylinders. So in the last term, we have studied thin wall cylinders. Okay, so now we study about the thick wall cylinders. So compared to thin wall cylinders, so in thick wall cylinders, the stress is not homogeneous throughout the thickness. Okay, so what happens is, in general, the inside material of a thick wall cylinder is more stressed than its outer parts. So in thin wall cylinders, the stresses are uniform, but in thick wall cylinders, the stresses inside is much more than the stresses on the outer part. So the stress difference increases with the increase in the outer to inner diameter ratio. So when we talk about the thick wall cylinders, actually, we'll be having this is the definition for the thick wall cylinder. So in thin walled cylinders, the ratio of thickness to radius will be less than 1/20th. Okay, so in thick wall cylinders, okay, we have done this in uh, solid mechanics too. So the longitudinal stress in a thin walled cylinders. So this is for thin walled cylinders. Okay, so you can have the stress in the longitudinal direction, and also you can have the stress in the along the hoop. Okay, so the longitudinal stress can be given as PDI over 2T. This one we did in last term, and the hoop stress can be given as PD over 2T. So this is the hoop stress. So the longitudinal stress will be half of the hoop stress. Okay, this is about thin wall cylinders. Now we'll be moving on to thick wall cylinders. So when we talk about thick wall cylinders, now we focus here. So you need to get familiarity with these things. One is the outer radius RO. Okay, so the other one is the inner radius RI. Okay, so this is the outer radius RO. Okay, so this is the inner radius Ri. Okay, so you will have the inner pressure Pi. Pi is the inner pressure. Now, PO is the outer pressure. PO is the outer pressure. Now, any distance within the cylinder, okay, any distance within the cylinder, we indicate with R. Okay, so R is the radius of any point within the cylinder. Okay, so this is your R. Okay, so the outer radius is RO, inner radius is RI. Okay, so inner pressure is PI, outer pressure is PO. So for thick cylinders, all right, I clear this. All right. So you can imagine the stresses acting on the thick wall cylinder. Okay. There will be radial stress. Okay. And there will be tangential stress uh, on the thick wall cylinder. So there will be radial stress and tangential stress, sigma theta. Now, the stresses acting on the thick wall cylinder, we can write the radial stress as simply easy to memorize. So C1 plus C2 over R square. So here you are referring R, any point within the cylinder at a distance R, the radial stress at a distance R within the cylinder. So this is R at a distance R from the center of the thick wall cylinder. The radial stress sigma R can be written as C1 plus C2 over R square. So this one we can also write in terms of this formula. Okay. So here now the Ri, capital Ri refers to inner radius. Okay. Capital Ro refers to outer radius. Okay. So just R refers to uh, the point within the thick wall cylinder, okay, where you are calculating the radial stress at a distance R from the center of the thick wall cylinder, okay, where you are calculating the radial stress. Okay, so Pi is the inner pressure, so PO is the outer pressure. So PO is the outer pressure. So you can see here the small r is the variable. So small r is the variable at any point r where you are calculating. So this sometimes we write as capital R or sometimes we write it as small r. Both represents the same thing. So they represents distance from the center of the cylinder where you are calculating the radial stress. Okay, so that is, you can see the small r here. Okay, so this is the radial stress. As you can see here, the radial stress here, the arrows are pointing towards the center of the thick cylinder. So then the circumferential stress or the hoop stress, sigma theta. So sigma theta, we call it as the hoop stress or the tangential stress. So we can write it as C1 minus C2 over R square. So all the terms will have the same meaning: inner radius, outer radius, inner pressure, outer pressure. So R is the point where you're calculating the tangential stress. So the distance to the point where the tangential stress is calculated. So the thick wall cylinders, actually cylinders are used mainly to carry out pressurized liquids. So they are subjected to high pressures inside. Okay. So as a result, so the stresses in the thickness will vary. Okay. There are two types of stresses. One is the radial stress and the other one is the tangential stress. So you can define the radial and tangential stresses. So in terms of the inner pressure, outer pressure, and also in terms of inner radius and outer radius. The derivation of these formulas, you can actually go through any standard textbook. Okay, the derivation is not important for us, and we need to study how to apply these formulas to calculate various stress conditions for thick cylinders. So when the cylinders are fully elastic, when the cylinders are partly elastic and partly plastic, and when the cylinder is fully plastic conditions. Okay, so the most important characteristics are inner radius, outer radius, inner pressure, outer pressure, and the variable R represents any point within the uh, thick cylinder where you are calculating the stresses. So for easy Um, for memorizing easily, you can write radial stress as C1 plus C2 over R square and tangential stress as C1 minus C2 over R square. So what is C1? C1 is R1 square Pi minus RO square PO over RO square minus Ri square. So you know RO, Ri are the inner and outer radiuses. Okay. So C2 represents Ri square RO square over RO square minus R square Ri square into the difference in pressures PO minus PI. Okay, you can see the formulas. All right. So when we talk about the thick wall cylinder, so generally we represent the thick wall cylinder like this. So inner radius, outer radius, okay, inner pressure PI. Okay, so the outer pressure is PO. So the two stresses we can radial stress and tangential stress. So when you want to represent, okay, you can represent as shown here. Okay, so the variation of radial stress. So the radial stress at the outer end of the thick wall cylinder will be always zero. So the minimum radial stress will be the outside of the outer radius of the cylinder, which will be zero. And the radial stress, maximum radial stress is at the inner walls of the cylinder, which is equals to the inner pressure. Okay, so the radial stress varies from negative pi to zero as shown like this. So always the radial stress is equivalent to the maximum value inner pressure at the inner radius. Okay, and the outer radius, the radial stress is zero, and the radial stress gradually decreases to zero from a maximum value of inner pressure Pi. Whereas the tangential stress, as you can see here, so the maximum tangential stress always occurs at the inner radius. Okay, at the inner radius, the maximum tangential stress occurs. But this stress will not be zero at the outer fiber. So at the outer radius, there will be still some amount of tangential stress left. Okay, so of course, at the outer radius, the tangential stress will be minimum. Okay, so the maximum tangential stress occurs at the inner radius. At the outer radius, okay, the tangential stress will be minimum but not zero. Okay, so it will not be zero, but it will be having a minimum value. Okay, so within the thick wall cylinder, so we can define the average tangential stress, sigma theta average. Okay, so the average tangential stress, we can write it as so we can write it as sigma theta average. So the value will be okay. So inner radius multiplied by inner pressure RIPI over the thickness of the cylinder. So the thickness refers to, so we can write the thickness of the cylinder as outer radius minus inner radius. Okay, So this is how we can calculate the average tangential stress. Guys, you can note down this formula. So sigma theta average is the average tangential stress within the thick wall cylinder. So you can write it as RIPI over the thickness. So thickness means the outer radius minus inner radius Ri. All right. So this is the average tangential stress. So maximum radial stress is equivalent to inner pressure Pi. Then the minimum radial stress is at the outer radius where it is zero. So the tangential stress is maximum at the inner radius, but it still retains some value at the outer radius. So within the fibers of the thick cylinder, so we can define the average tangential stress as RIPI over the thickness, that is outer radius minus inner radius. All right. So now let us go through the formulas given in your learning guide. So the maximum shear stress you can write as okay. So the maximum shear stress you can write it as tau max. So which is we ignore the sign. We'll take the magnitude only. So the maximum shear stress is so magnitude half of the difference of tangential stress and radial stress, sigma theta minus sigma r. So this is the maximum shear stress. So I just read it on the formula, that's all. Okay. So if you substitute sigma theta and sigma r values, so you can write the maximum shear stress as magnitude of C2 over R square. So if you write C1, C2 values and you can see the difference, so you can calculate, you can cancel this C1 and C1. So therefore you will get the maximum shear stress as C2 over R square magnitude. So if you replace C2, then the formula for the maximum shear stress will be this. All right. So you can write down the maximum shear stress formula for the thick cylinder like this. So you know formula for the radial stress, you know the formula for the tangential stress. Okay. You know the formula for the maximum shear stress, and you know the formula for the average tangential stress, sigma theta average for thick wall cylinders. All right. Sorry. Okay. Uh, so now we can see the stress distribution under extreme conditions. Okay. So when the inner pressure is greater than outer pressure, when the inner pressure is greater than outer pressure, so you can write the radial stress, okay, in terms of the yield stress. Sigma y is the yield stress, sigma y. Okay. So when the maximum stress, shear stress is half of yield stress, okay, when the inner pressure is greater than outer pressure, the radial stress can be given by this expression. So similarly, the tangential stress sigma theta can be given by this expression when the inner pressure is less than outer pressure. Pi is less than outer pressure, PO. Okay, so what we are doing is under different conditions now, under extreme conditions, so how the radial stress and tangential stress varies within the cylinder, thick wall cylinder. Okay, so when the inner pressure is greater than outer pressure, when the inner pressure is less than outer pressure, the radial and tangential stresses. All right, so now before going to further discussing the elastoplastic behavior of the things, we can look at, we'll go through this probably tomorrow. Now let us look at the first question. So this question is actually a worked out problem in a number of books. So here what it shows, it asks you is, show that the ratio of the maximum tangential stress to the average tangential stress, okay, for a thick wall cylinder subjected only to internal pressure is, so you can write as 1 plus lambda square over 1 plus lambda, where lambda is nothing but the ratio of the outer radius to inner radius. So that means we are asked to prove what is the ratio of the maximum tangential stress. So sigma theta max over sigma theta average. So sigma theta max over sigma theta average. So you're asked to prove that this ratio can be written as 1 plus lambda square over 1 plus lambda. So where lambda can be the ratio of, okay, so lambda is the ratio of outer radius over inner radius, Rho over Ri. So this is applicable for all thick wall cylinders. So the ratio of maximum tangential stress over the average tangential stress can be written in terms of the ratio of the outer radius and inner radius like this. Okay, so to prove this, then we need to find out what is the maximum tangential stress. So the maximum tangential stress occurs, so sigma theta maximum occurs when, so the maximum tangential stress occurs, of course, at inner radius, so where the variable r is equivalent to the inner radius, and the maximum tangential stress occurs also when outer pressure is zero, when outer pressure is zero. So the maximum tangential stress always occurs when at inner radius and also when the outer pressure is zero. So we use these two conditions, okay? So the maximum tangential pressure occurs at inner radius and when the pressure, outside pressure is zero, then we know what is the formula for sigma theta. So we know the first slide we have seen. This is the formula for sigma theta. Okay, so we know sigma theta, this formula. So now in this formula we substitute, so instead of R, okay, we substitute Ri. Okay, so and we substitute, instead of P naught, we substitute P naught is equal to 0. Okay, so then this tangential stress becomes sigma theta maximum. So to get maximum tangential stress, we replace the R with inner radius and we replace outer pressure with 0. So from the basic formula. Okay, so from the basic formula, we do this, then we get sigma theta maximum. Then we know what is sigma theta average. So sigma theta average is nothing but so inner radius multiplied by inner pressure Ri Pi over thickness. So over thickness is Ro minus Ri. So outer radius minus inner radius. Okay, so once we take the ratio of these two terms and simplify, then we should be able to write the required equation, whatever the resulted equation. So in terms of this formula, 1 plus lambda square over 1 plus lambda. So, okay, so I can show you here. So now sigma theta average we have seen. So RIPI over the thickness. Okay, and the maximum tangential stress occurs, okay, when the R is at inner radius and when the pressure is outer pressure is 0. Okay, so now from the formula we replace R with Ri square, R square with Ri square, and we replace P naught with 0, therefore it becomes negative Pi. So this formula, when you simplify, you will be able to write in this form. So we're just rearranging the terms. Okay, so you can cancel out this Ri and Ri. Then whatever the resulting equation, we can rewrite in this format. So that is sigma theta maximum. So then sigma theta average we know is this. Okay, so when we take the ratio of sigma theta over sigma average, okay, so we got the two expressions. So this is sigma theta max, so this is your sigma theta average. So if you take the ratio then simplify, so we'll be able to write in this form, so we can get the final answer like this, and we replace lambda with Ro over Ri. So lambda is replaced with Ro over Ri. So this result is basically tells us that this ratio, the maximum tangential ratio over the average tangential stress ratio depends on the outer radius and inner radius ratio. Okay. So then you need to plot this in terms of lambda. You can take lambda here. Okay. So then you can take percentage here. Then take different values of lambda. So choose different values. Let us say 0, 2, 4, 6, 8. Then calculate what will be the eta. So eta is nothing but the ratio. So eta is nothing but sigma theta max over sigma theta average. So calculate and plot the values in an XY plot as shown. Okay. So you can say as the ratio increases, so the ratio of maximum stress over average stress also gradually increases like this. All right, so this will be your first question. Any doubts? All right, the Kasi says no. How about other things? Yeah. So here, the derivation part are other things you can read from books. So what is important is, so for a thick wall cylinder, how the tangential stress, how it varies, how it is connected with respect to inner pressure, inner radius, and outer radius. So similarly, radial stress, how it is connected with those parameters. Then what is meant by average tangential stress? Okay, so then for this problem, we are just doing theoretically. So what will be the ratio of the maximum tangential stress over the average tangential stress? So this is just, we can write in terms of the ratio of the outer radius and inner radius. Okay, so all right. So the next problem we'll see, it's quite simple. So that's why we finish this and close the session. So this question says, show that no matter how large the outside diameter of a cylinder, subjected only to internal pressure, so whatever may be the outer radius, okay, so the maximum tangential stress is not less than, so maximum tangential stress is cannot be less than inner pressure, cannot be less than. So I just cancel this, cannot be less than inner pressure. So what are maybe the outer radius of the cylinder, outer diameter of the cylinder, or outer radius of the cylinder? So we need to say that the maximum tangential stress will be always, okay, cannot be less than inner pressure. It is more than uh, inner pressure. So the ratio, the maximum tangential stress will be always greater than inner pressure. So irrespective of whatever may be the outer radius. So here this one basically tells us that it is not ideal to just increase the thickness of a cylinder to reduce the tangential stresses, because whatever may be the outer radius, the tangential stress cannot be reduced below the inner pressure of the cylinder. So the pressure and stresses, they are the same units and same concept, right? So now let us prove this. It's quite easy to prove this. So we can write the maximum tangential stress as you can see here. So we can write the maximum tangential stress, okay? We can write from this formula, okay? So the maximum tangential stress occurs when R is equal to Ri, and when outer pressure is 0, when outer pressure is 0. So the first formula, the first question we have seen this. So this expression we can write in this format. Okay, both are equal. Okay, so now we focus on this expression. Okay, so now what we do, we say outer radius is, let us say, 2 times inner radius. So we say outer radius is 2 times inner radius. Then we calculate what will be the maximum tangential stress. Okay, so we replace Ri with, Rho with 2 times Ri. So that means when you replace Rho square, so you will get 4 Ri square. Okay, so 4 Ri square. So here also we replace Rho square with 4 Ri square. So everything is in terms of Ri. So now you can cancel out. So this will become 5 Ri square. So you can cancel Ri square, and here 4 Ri square minus Ri square, it becomes 3 Ri square. So you can cancel again this. Okay, so here you can cancel Ri, you will get. So basically the ratio, the maximum tangential stress, you can write pi by 3 times Pi. This is when the outer radius is 2 times the inner radius. So next we take outer radius as 3 times inner radius, 3 times Ri. Okay, so again in this formula we replace Rho square with 9 Ri square. Okay, so Rho square with 9 Ri square. So 9 Ri minus Ri square, so you get 8 Ri square. Okay. So Rho square over Ri square. So here 9 Ri square, so you get cancelled. So 1 plus 9, it becomes 10. So you still get the ratio sigma theta max. Okay, the maximum tangential stress is 10 by 8 times Pi. So this is definitely greater than Pi because it is greater than 1. So here also it is greater than Pi. So like this, if you keep on increasing the outer radius, okay, whatever may be the number, okay, so whatever may be the number, the maximum tangential stress sigma theta max, so we can simply write like this. So we can simply write like this: n square plus 1 over n square minus 1. Okay, so n square plus 1 over n square minus 1 will be always greater than 1. Okay, so therefore, whatever may be the outer radius, so the maximum tangential stress will be always greater than Pi. So where is inner pressure? So that means it is impossible to build a thick cylinder so that you can reduce the maximum tangential stress with less than the inner pressure of the cylinder. It is not possible theoretically. So tangential pressure stress always will be greater than inner pressure. All right. So we'll stop here. We'll continue in the next session. There are 2 more questions. Those are very important. And the first 2 questions will now be asked in the exams. So this is just for conceptual understanding and to understand the behavior, theoretical behavior of thick wall cylinders. All right. So I stop the recording now. Guys, any questions, let me know. We have some more time. So please get prepared for the Sunday mechanical vibration class test and take note of the timing, 3 to 4:30. I'll be discussing about the type of questions in the next session. All right, so that part we'll deal tomorrow, the class test part. Then solids, we are almost completing the topics except the 2 more questions related to thick wall cylinders, and those 2 questions are very important because one of the question will be normally asked in the exams, and that question carries more weightage compared to all other questions, and it is always easy to score because that question is very simple and also easy to score full marks. Okay, so next week when we meet, we'll complete the thick wall topics, and if time permits, I'll also go through normally different type of questions that may be asked in the end of term exams. All right, I'll stop here. Let me know if you have any questions or any